Hey everyone, this is Daniel, and this video is a replica of a conference talk that I held at Scala 2024 titled Generative Art with Scala, No AI Required. This is essentially a glorified version of creative coding with Scala and functional programming, which is why I titled this video Artistic Scala. In this video, you're going to learn some graphical utilities of functional programming, including some Perlin noises and a bunch of techniques to create some artistic output. Now, the Git repository for the conference talk, as well as the one for this video, you can find at github.com/rockthejvm/Scala2024 Artistic Scala. This is the name of the Git repository. And I'm also going to share a link in the description of this video. Now, the code in this Git repository, as well as the code that we're going to write in this video, will allow you to create something like this, where you have a particle field that will gravitate towards some shapes that the webcam of your computer is going to catch dynamically. So this is not necessarily a static picture, but it's a dynamic animation that a Scala.js application will generate for you in real time. And this is only a screenshot of what you'll be able to obtain. So in this video, you're going to learn the techniques and the principles behind generating a picture like this, which I think would be quite hard to explain to an AI. This repo also has some instructions on how to run this locally if you want to replicate or if you want to change this code as you see fit. All right. Now, after you clone and open this repository in your preferred development environment, you'll get to a piece of code that looks something like this. So this is the only Scala source that we have so far. I'm going to take a minute to describe this sort of project if you're unfamiliar with Scala.js, which is what we're going to write in this video. So this is a regular SBT project that you're probably familiar with from the JVM world. So here under build SBT, I have a project called app, which you can find in the directory app in the project Scala 2024. And this has a bunch of library dependencies, currently has laminar, although laminar isn't really necessary for this video. You can even cut it out if you want. And we have a bunch of settings that will allow Scala to be compiled or transpiled to JavaScript, which is why I enabled the Scala.js plugin here. And you can find the Scala.js plugin configuration here under project plugins SBT, which is where you will find a bunch of SBT plugins. That's not really necessary. You don't have to touch build SBT or plugins SBT. This is just for you to know that this is a Scala.js project instead of a Scala JVM project, which is the majority of the videos on the channel. So you can navigate to the app directory where we're going to store the code for this project. And under source, we have the regular source main Scala files that we normally have in a JVM application, and we have an object called Scala 2024, which is a regular main application with a def main that you're used to from the JVM world. I have a bunch of variables that I'm going to describe shortly, but ignore this for the moment. Now, besides the source directory, we have a bunch of JavaScript-related directories like parcel cache, dist, node modules, and these are described in package.json. If you're unfamiliar with frontend, package.json is the equivalent of build SBT for JavaScript. And we have some dev dependencies in which we can have some JavaScript libraries that NPM can download from the NPM repository, like we do for Maven on the JVM. So this is very easily equivalent, as well as some scripts or some actions that you can run from this directory. For example, if I do npm run start, this will run a web server called Parcel that will take this index.html, which I've described here in the folder, and it will serve that as a local dev server. And speaking of index.html, this is a plain HTML file where the div ID app is where we're going to have the contents of the application. And the contents of this application are going to be the canvas that we're going to draw things on. And this is where our absolutely magical artistic output is going to stay, as well as some auxiliary tags that we're going to use to capture images from the webcam. And this will alter what we are going to display on this canvas. So from this index.html, we only care about the canvas. Now, if you're following along and if you're running this for the first time, I recommend that you open a terminal and do two things. First, I want you to open an SBT console, so do SBT. And in another terminal, go to the app directory and run npm install. Those of you coming from JavaScript or from front end will run this almost by instinct, so do an npm install first and run an SBT console in another terminal. Okay. After you've run that in the SBT terminal, go to the app directory or to the app project in SBT. So do project app and do tilde fast opt.js. This is a tilde compile equivalent for Scala.js, and this will look at every source Scala file in the source directory, and it will transpile that to JavaScript. So do fast opt.js. And in the other terminal, after you did npm install, do npm run start. So the way that this terminal environment is going to work is that as you change your Scala file in the source directory, the first SBT terminal is going to catch those changes and recompile your code, which will run or output some JavaScript that the other terminal will catch and reserve your page at localhost 1234. So if I go to localhost 1234, I have a plain canvas here, plain white canvas that we're going to use to draw things. Now, in my opinion, a white canvas is artistic enough, so you can stare at this white canvas and contemplate on the meaning of life if you want, but we're going to draw something that's a little bit more interesting. Okay, so I'm going to go back and I'm going to minimize my terminals here because I don't care about them anymore. I'm going to close my index.html, and we're going to start spending all of our time, or all of our remaining time in this video, in the Scala 2024 object. So right now we have a bunch of variables that I'm going to describe in due time. Currently, the first set of variables refer to the HTML tags in index.html. So we have the display canvas, the off-screen canvas, and a video element that we're going to use to capture webcam pictures. We're going to first refer to the display canvas and start drawing some stuff. So here I'm going to create a little method. Let's call this make good art. And this refers to the absolutely amazing Make Good Art commencement speech by Neil Gaiman. If you want to check that out, it's an amazing piece of philosophy if you are interested into that sort of thing. So make good art. This is going to take the display canvas and it's going to draw some stuff. Now, what am I going to draw? I'm going to draw some particles that are going to move in some sort of a magnetic field. And this magnetic field is going to be computed in a particular way. I'm going to walk you through step by step. So first, I'm going to describe this magnetic field into a grid. A grid will describe some angles in which the particles are supposed to move, or towards which the particles are supposed to move. And that grid is going to be an array of 100 by 100 angles in which the particles are supposed to move on screen, and the grid, or the magnetic field, will describe the trajectories of the particles as they arrive in those particular grids. So it's as if this canvas is split in a grid of 100 by 100 cells, and every cell is going to have an angle that will direct a particle that is going to be staying in that cell. So I'm going to generate a grid. So I'm going to have a function. Let's call this make random field. And this is going to be a unit function that is going to take this grid and randomize that with an angle between 0 and 2 pi for every position of this array. So I'm going to have a for loop here. So I'm going to have a row in between 0 until grid size, and column in 0 until grid size. And here I'm going to do the following. I'm going to say grid of row and column is going to be random number. So I'm going to say random dot next, or next double. That's going to be a number between 0 and 1. And I'm going to multiply that with a 2 pi, which describes the entire circle. So the entire circle has 2 pi radians. So I'm going to say 2 times math pi. So random next double times 2 times math pi, and this will be the angle of the grid at this particular row and column. And at this particular row and column, just to show you how that would look like on the canvas, I'm going to draw some arrows. So in this make good art, I'm going to say make random field. So make random field. And then I'm going to take all the items in the grid and I'm going to draw an arrow at that position. So what I'm going to do is I'm going to run another for loop. I tend to not do for loops too much, but in this case, because we're dealing in mutable arrays, we're going to run for loops here. And I'm going to use a little thing called tools, which I also added in the Git repository. And here we have an extension section for the canvas rendering context 2D, which is a JavaScript data structure that describes the capability of drawing things on a canvas. And I added a little method here in Scala.js called draw arrow at these coordinates at a particular length and with a particular angle. And this procedural function is going to simply move the context in certain positions, and it's going to draw some lines. Finally, it's going to set the stroke style to black, and then it's going to stroke at the path that I've just described in the previous instructions. So if you're interested, you can check out this little draw arrow function if you want to learn more about it. So I'm going to say context, which is here. I'm going to say context. And I'm going to say context.drawArrow. If you don't have the draw arrow extension method, I recommend that you import the tools. So you have an import here in the object. So I'm going to say draw arrow at row and column. Now at row and column, I'm going to have row times, and we have the grid dimension here, which is called resolution. So I'm going to say row times resolution and col times resolution. The length is going to be the length of an arrow, like step length. So I'm going to say step length. And the angle given by the grid at that particular position. So I'm going to say grid at row and column. That's going to be the angle at which I'm going to draw that particular arrow. So in main, I'm going to say make good art, which is not really good art yet, but it's going to do something. Just to make sure that this thing works successfully, it needs to compile the code, and it needs to refetch or re-render things on the screen. And look at this. We have arrows being drawn on the canvas, and these arrows look a little flat because I've stretched the canvas in 100 by 100 cells. But look at these arrows. They seem quite random, which is roughly in line with what we expect. Now, if I lay a little particle here and I make it run in the direction of these arrows, because the arrows are quite random, the particle will simply move back and forth roughly in the same spot. And I'm going to run a little magnetic field, or these arrows, such that they're not really all that random. I'm going to make these arrows random but smoother, in the sense that for adjacent positions, the arrows are going to be slightly divergent, not very wildly divergent. And this sort of noise, or this sort of random noise, is very useful in graphics programming, especially in video games. And one example of this randomized smooth noise is called Perlin Noise. So I'm going to use a Perlin Noise field instead of random next double. So I'm going to say Perlin, which is another file that I added in the Git repository, perlin.noise2d. And noise2d is a function that takes two arguments. So noise2d takes two arguments in the form of doubles, and they can have arbitrary ranges. And this noise2d is always going to give you back a number between 0 and 1. The way that Perlin Noise works is that we're going to have a permutation array, and we're going to run some interpolation between the values of adjacent coordinates. The theory behind that is a little bit more complicated, and I'm not going to delve too deep into this. You can take a look at the noise2d function if you want. But the noise2d property is a doubly differentiable function such that the variation in inputs is going to be proportional to the variation of outputs and vice versa. In other words, for very adjacent positions, the arrows are going to be only slightly angled. So if I do Perlin Noise 2D, and I'm going to say row and col, and I'm going to have row multiplied by a little factor that's going to minimize its contribution a bit. So I'm going to say 0 times 0.005 and col times 0.005 times 2 times math pi. If I save that, look at the arrows. The arrows are not really that far apart. They're quite aligned now, but they're also varying. So if you take a look at the canvas, as we move towards one edge of the screen, the arrows are slightly going to be inclined towards each other, which means that if I leave a particle in any one position and I leave it into the flow field of this magnetic field, it's going to move in a pretty interesting direction. So I'm going to ignore, or not going to draw the arrows themselves, but I'm going to leave a particle somewhere on the screen. I'm going to show you how that is going to move in the direction of these magnetic fields. So I'm going to use Perlin Noise instead of random, such that I'm going to render some particles in a nice direction on the screen. So I'm going to change my code a bit. I'm going to define a new function. Let's call this draw particles. And I'm going to have my particles as a list of positions. And these positions are going to be coordinates on the canvas. So that's going to be an XY, so double double. And this is going to be a unit function. All right, now I have to generate a bunch of particles initially. So in my make good art, instead of running my for loop in which I'm going to draw arrows, I'm going to move my make random field inside the draw particles method. And in make good art, I'm going to initialize a random list of particles. So I'm going to have my particles and I have a variable here, a number of particles. You can tone that down, for example, to 500 first, because if you increase the number of particles, that will increase the amount of time for rendering. So I'm just going to keep it low, and my particles is going to be 1 to a number of particles, and this is a more functional approach, map, and for every index, I'm going to have a val x as math random times either math random, or you can use a random variable here. So math random times display, and we have display width, and val y is math random times display height. So this is going to be a random coordinate at the start of the particle. And I'm going to return x and y as the tuple. And then in make good art, I'm going to say draw particles as particles.toList. That's going to be my first draw. So in draw particles, now I can focus on this function here. So I'm going to make the random field. So in draw particles, what I'm going to do is I'm going to make my canvas, instead of white, I'm going to draw it black for a more dramatic effect. So I'm going to say context.fill style is equal to black, and this is a very JavaScript-like association here. Then I'm going to have context.fill rect, or filled rectangle, 0, 0, display width, display height. And this is going to be filling the entire canvas with black. If I save this, then we're going to have a black canvas. All right. And then I'm going to find out where my particles are going to be next. So I'm going to have val new particles as particles map. And in case we have xy, then I'm going to try to figure out where the next xy position is going to be given the grid row column at that particular position. So first, what I'm going to do is I'm going to compute the row and column of this particular particle at this particular position. So I'm going to have my row, and the row is the vertical position. So I'm going to divide. So I'm going to have y divided by resolution, which is the grid cell size. So y divided by resolution, and then I'm going to convert that to an int. So I'm going to find the cell coordinate of this particular particle. Same with the column as x divided by resolution, and then I'm going to have to int here. And I'm going to regenerate the particle if the row and column is outside the canvas. So if the row is bigger than or equal to 0, and row is less than the grid size, which is the maximum cell count. So if row bigger than or equal to 0, and row less than grid size, and same for column. So and column bigger than or equal to 0, and column less than grid size, then I'm going to figure out where the next coordinates are going to be. So I'm going to have x plus, and I'm going to figure out what the angle is there. So I'm going to have val angle is given by the magnetic field at the cell coordinates, so grid row column. So this is going to be the angle. And then I'm going to have to compute the new x and new y given a particular step. And I'm going to increase the particle step by 5. So I'm going to make the particle move by 5 steps. So I'm going to say x plus step length times, and there is cosine of angle. For those of you trying to brush up your physics, you can contact me after. Then y plus step length times sine of angle. So this is how you can obtain the next positions given the angle at the current positions. So this is going to be the new position of the particle. Otherwise, I'm going to recreate it randomly on the screen. So I'm going to have math random times display width and math random times display height. So I'm going to regenerate the particle randomly on the screen if it just got out of the canvas. So the new particles is going to be another list of new positions. Okay, so what I'm going to do now is I'm going to draw a line between the particle and the new particle. So I'm going to say particles zip new particles, and then for each, I'm going to have a case for a nested tuple. So I'm going to have x, y, and then new x and new y. And I'm going to draw a line between these two positions. So what I'm going to do is I'm going to have context dot begin path, and this is the JavaScript way of drawing things on the canvas, and this is mirrored in Scala.js. So I'm going to say context begin path context dot stroke style is equal to, and I'm going to use a CSS color there. So I'm going to have 0x0080ff. So this is kind of like a cyan color. So context stroke style is going to be a green bluish color. Then I'm going to have context line width is equal to 1, and then context move to the original coordinates xy, context line to new x and new y. At this point, I've described a path, and then I'm going to say context.stroke to draw a line or draw the path that I've just described by moving and lining. So in this case, I'm going to draw a line between these particles. So what I'm going to do is I'm going to save, and what you're going to see is just a bunch of nothing here on the canvas. And my guess is because the lines themselves are also black. So if I do this in white, yeah, look at that. Look at my particles. Their particles are all black, and that's because my CSS color is not 0x00 whatever, it's hash 0080ff. So this is the CSS color. The 0x is the JVM style of writing an integer, which is something that I apparently have a reflex writing. So I'm going to change my background to black again. And the CSS color is this little guy, 0080ff. I'm going to save that and look at my particles. They seem to be moving somewhere along the screen, but they're frozen. So I'd like to animate that. So what I'm going to do is after the particles, I'm going to run a JavaScript API called a request animation frame, which in Scala.js is dom.window.requestAnimationFrame. And the callback is a simple Scala function to draw the particles at the new positions. So new particles. Now, if I save that, we're going to see these particles moving across the screen with a bunch of extra hashes across my screen there because I haven't taken into account some things, which is, for example, the fact that when the particle is re-rendered on or reset in a random position on the canvas, I'm going to essentially draw a line between the old position and the completely random position that the new particle is going to have. So I'm going to filter this thing. So I'm going to say filter, and I'm going to have my same case. So filter, and I'm going to have a similar case there. And I'm going to have my for each after that. So in case we have x, y, new x, and new y, the filter for that is going to be that the distance between x and new x and y minus new y is not going to be bigger than the step length. So I'm going to have my math abs between new x minus x is less than or equal to step length. And math abs for new y minus y is also less than or equal to step length. So I'm not gonna have all these hashes across the screen. So if I save this, hopefully the code will compile, and look at my particles. They're flowing nicely in the magnetic field described by the canvas. And that magnetic field is described randomly at every refresh of the page. So look at that. The magnetic field converges these particles into one position, and the particles go in the direction of the magnetic field. Obviously, if you increase the number of particles from 500 to 5,000 or something like that, you're going to see a much better description of how the magnetic flow works. So that's going to be quite interesting. Now, what I'd like to do is I would like to create not only simple particles, but I'm going to describe snakes of these particles. So the historical positions where these particles have been in space. That's going to be a more complicated endeavor. So I'm going to tune my number of particles down to 500 again. So we're going to have an easier time rendering things on screen. And I'm going to change my draw particles function from a particles list of just simple coordinates to a list of snakes So a list of lists of coordinates. So my code is not going to compile for a while. So I'm going to have a list of lists of double double. And every segment of that particular snake is going to also have an integer property there, because every segment in the snake is going to disappear after a while, and the int is going to keep track of how long a segment is going to be present on the screen. So my code is not going to compile for a while. So this is going to be my particles, and I'm not going to name this particles, but rather particle trails. And my new particle positions are going to be obtained by particle trails.head. So the particle trails.head is going to contain the list of the heads of all the snakes. So I'm going to have particle trails head map, and in case we have x, y, and something, I'm going to obtain the new coordinates there. Now, the age of the particular segment there is also important, because I would like to reset a particle on the screen if the age is too big, which is why I've constrained the maximum age of a snake to this max age parameter. You can play with this parameter if you want to make longer snakes by increasing it, or shorter snakes by decreasing it. So I'm going to take the filter here to reset a particle on the screen if the condition holds true, and also if the age is less than max age. If any particle is bigger than max age, then I'm going to reset it on the screen. Okay, so these are the new particle positions. Then I'm going to have to compute the new particle trails. So the new particle trails, and have new particle trails, is going to be the following. If the particle trails dot length is bigger than or equal to max age, or I'm just going to use the strict, it's not really all that important. So it's bigger than max age. So if the particle trails is bigger than max age, I'm going to cut out the last piece of the particle trails and put out the new heads of the particles. So I'm going to have new particles. Awesome. Now, the drawing of the snakes is also going to be a little different now, although the filtering and the for each is going to keep staying relevant here. But the data that I'm going to mangle with is going to be a little bit more complicated, because I have lists of lists this time. So I have to be careful what I'm doing with. So I'm going to have my new particle trails. So new particle trails will be the new snakes. So I'm going to have new particle trails in it, zip with the old particle trails, which is new particle trails.tail. So this is going to be all the segments of all the snakes of the new particles. And then I'm going to say zip with index, which also contains each individual particle's age. I'm going to have dot for each. And then I'm going to take the filter and the for each out. I'm going to cut that. I'm going to make sure that I paste it inside and comment that out. And in case we have a list of new positions, old positions, and then the age. So this is going to be a nested tuple, because the new particle trails zip with the new particle trails tail is going to be new positions, old positions, and zip with index is going to have the age at the last. So this is going to be the last member of the nested tuple. Then I'm going to have my new positions, zip old positions, and then I'm going to run the filter and for each I used to work with in the previous case. So I'm going to have filter and for each. Now, the code will not compile because we have the new positions as a list of double int. So I'm going to have to swap these arguments around. So new x, new y, and new age. And then x, y, and the old age. I'm going to have math abs new x minus x. So the filter here is going to still stay relevant. Okay. Then I'm going to have my for each, and I'm going to have the same argument swap, new x, new y, and age, and x, y, and whatever, because this thing is going to be age minus 1. Then I'm going to have begin path, stroke style, line width, move to, line to, and stroke. Hopefully my code compiles, but I don't think it will, because my new particles is now new particle trails. And apparently the code still doesn't compile. So we have new particle trails, list of, what is thing? Double int, particle trails, new particles is going to be list of double. I forgot the age. So this is age plus 1 when I create the new segment, and age is going to start at 0 when I reset the particle on the screen. So make sure you add the third argument here in the tuples when you build the new particle elements. All right, new particle trails is going to be a list of double int, which should compile my code and should compile my last draw particles function when it's going to be invoked by the browser. Okay, now finally in make good art, when I'm doing draw particles, I'm going to wrap that in a list, and that should be it. The code still doesn't compile because I'm going to have the age thing. So I'm going to have math random times max age, and I'm going to wrap that in an int. I'm going to have 2 int here, and I'm going to have my age. So I'm going to have to create a triple here, not a pair. And at this point, look at that. We have particles as snakes that are moving in the direction of the magnetic field. And this looks pretty cool already. If you increase the number of particles, I have currently 500. Maybe if you double that, maybe make 1,000. And this looks quite nice. And the magnetic field is going to be regenerated randomly on every page refresh. This is absolutely fantastic. If you also want to create snakes that are varying in color, I also gave you a little tool. So in tools.scala, I have a little function to interpolate a color. So with a value between 0 and 1, between 2 colors expressed as an integer, as CSS colors. And you can interpolate those. So if I go back to my Scala file, instead of having a static color, you can use lerp color fade. And the value is going to be given by the age. And the age is going to be age times 1.0 divided by max age. So that's going to put this age in between 0 and 1. And the CSS color is going to be described as an integer. So I'm going to have a 0x this time, so not a CSS hash. So I'm going to use 0080ff. So that's the bluish color that you saw earlier, and maybe a pinkish color. So that's going to be 0x8000ff. So the blue thing is going to still be the same. So look at that. We have these purple-like particles that are moving on the screen, and they also have some transparency to them because the lerp color fade also has the alpha channel described by the age. So the snake is going to be a little translucent in there. So look at that. We have pretty artistic output already, in my opinion, if you want to look at this sort of animation. So at this point, we've fulfilled every programmer's dream, which is to be able to create your own screensaver. But that's not all, folks. I would like to recreate the magnetic field by taking some input, some external input, rather than just the Perlin noise that we created earlier. So the Perlin noise 2D is a statically generated random flow field that has some random values that are smooth as described by these particles. I would like to change the Perlin noise to something that also takes another non-spatial coordinate, maybe the time coordinate. So in the make random field, I'm going to have a time parameter. So I'm going to have, let's say, date.now. This is the JavaScript date. And I'm going to multiply that by a very, very small amount, like 0.0001 or something like that. I'm going to use Perlin noise 3D instead of 2D, which takes 3 coordinates instead of 2. And the nice thing about Perlin noise is that the coordinates do not necessarily have to be spatial coordinates. With spatial coordinates, you can create volumetric things like liquids and smokes, like volumetric smokes in video games and things of that sort. Now, the third coordinate that I'm going to use is this time coordinate. It's not a spatial coordinate, so I'm going to have my time here. And this time is going to alter the direction of the Perlin noise. So I'm going to go ahead and save that. And if you take a look at, or if you wait for a bit to see how this Perlin noise changes, you'll see that the direction of these particles is going to change quite a bit if we wait long enough. Now I'm going to increase the input of time here just for you to see how these particles change in time. So look at that. Look at how the magnetic field changes with the direction of time. So these magnetic fields are going to be altered by the time coordinate, and the rivers that you saw on these particles are going to be altered in some chaotic fashion. So if you're mesmerized by this, you can take a look at this and stare at it all day. Now, this is nice enough. What I would like to do now is to create the third dimension or the third coordinate of the Perlin noise, not necessarily something that moves continuously, which changes the direction of the Perlin noise also in a smooth manner. If we break the property of the Perlin noise in that it's smooth, we can also obtain some pretty artistic things. And if I use, for example, the webcam picture does not necessarily have to satisfy that property that the image is going to be smooth across the board. So for naturally occurring edges in the images captured by the webcam, we're also going to see ruptures in the Perlin noise, which will converge the particles across edges. So I'm going to show you how we can do that. Now this part is a little bit tedious, especially at the beginning. So I'm going to run a small function called start video. And this is going to run a JavaScript API, obviously exposed as a Scala.js thing. So I'm going to use DOM window navigator media devices get user media, and we're going to add a little object called media stream constraints, which will describe the video output. So I'm going to have new media stream constraints, where I'm going to have this .video. So I'm going to add or make the browser request video from the device. So this video is new media track constraints, and I'm going to have the width of that is going to be 100 and height is going to be 100. So I'm going to capture video in 100 by 100 pixel resolution. So DOM window navigator, this sort of thing, returns a JavaScript promise, which has a method called then, which we wrap in Scala via backticks. So then, and I'm going to consider the stream that I'm going to capture from the video. And I have an HTML tag called video. So I'm going to have video dot source object is equal to stream. So the data stream that the browser has caught from the webcam, I'm going to display that in the video element on the index.html. And then I'm going to say video.play. So for now, I'm going to use this function. You can pause the video to take it to your own code if you're following along. And the start video, I'm going to call that in my main function. So I'm going to say start video and then make good art. So I'm going to save this. And at this point, the browser is going to allow or ask for webcam permissions from my webcam. So I'm going to say allow this time. And at this point, my webcam has started running, but it doesn't display anything on the screen. And that's natural because in the video element, I'm going to draw the video itself on another canvas, which I called the off-screen canvas, which is the second canvas that we have in the index.html. The video is going to take data, and I'm going to render whatever the video has for me, like images, on the off-screen canvas. So this off-screen canvas is going to show me the images caught by the webcam. Now, what I'm going to do is also a little bit more tedious. So in make random field, so in this make random field a function that creates the Perlin noise magnetic field, I'm going to obtain the brightness of the pictures caught by the video. In order for me to do that, I need to render the data from the video onto this off-screen canvas. So what I'm going to do is I'm going to clear the canvas first. So off-screen context, clear rect, 0, 0, and then I'm going to say off-screen canvas width, off-screen canvas height. So I'm going to clear that. Then I'm going to draw on it. So I'm going to say draw image, and you can draw static images or you can draw dynamic images like the video. So 0, 0, and then the same coordinates, off-screen canvas width, off-screen canvas height. So I'm going to draw things onto the off-screen context, and then I'm going to extract the image from this off-screen context in the format that I can take pixels. So I'm going to have my image data as off-screen context.getImageData. So the canvas is very useful for also extracting image information. So I'm going to say 0, 0, and then I'm going to have the same coordinates, off-screen canvas width, off-screen canvas height. It just happens that the off-screen and the display canvas both have the same coordinates, or the same dimensions. So that's going to be good for us. And then I'm going to have a brightness matrix and I have a little function called calculate brightness on this image data. So this brightness matrix is simply an array of doubles, and the double is going to be the brightness of the pixel caught at that particular coordinate. And the brightness matrix is going to influence my Perlin noise. So instead of time, I'm going to use the brightness matrix at that particular coordinate. So I'm going to have my let's call this scaled brightness, as brightness matrix of row and column. And I'm also going to multiply that by 0.002 or something like that. So a small multiplier there. So scaled brightness is going to be my third coordinate of my Perlin noise function. So this is not going to be smooth anymore because the brightness matrix doesn't really follow the same smoothness property, given that the images from the camera can be completely arbitrary. So let me go to my web page, and at this point, you can see me at the top left corner recording the video that you're watching right now, and the Perlin noise is a little bit more drastic this time. But this also takes the shape of whatever is moving on the screen. So if I have my hand here, that is going to influence the Perlin noise field or the particles. So if you refresh the page, you're going to see these particles moving in a seemingly random fashion. And I'm going to change these parameters a little bit. I'm going to make the coordinates have a little bit less of an input, and the brightness is going to have more of an input. And I'm also going to render a bit more particles, like 2,000 particles, so that we can obtain some more interesting pictures. So look at that. Now, as my webcam is starting to capture images, and if the canvas is square, you can obtain some more interesting pictures. And I tend to like this quite a bunch. All right, so that is it, folks. So there you have it, folks. Just about 100 lines of Scala.js is able to generate some algorithmic art that is very hard to describe to an AI. I hope you enjoyed this video. If you did, click the like button for me and subscribe to the channel for more videos like this. Check out my website at rockthejvm.com. I have literally hundreds of hours of everything in Scala, Kotlin, and everything in between. Until next time, folks, this is Daniel signing off.